Welcome to Deep Dive into Applied Science. This is our very first episode and we're here with Abra.
Hi, my name is Abra Ahmed. I'm currently doing my PhD here at the Hochschule Trier in collaboration also with the University of Trier. I'm doing my PhD in the area of applied statistics and data science, working with large language models, as the buzzwords go.
Large language models or AI are everywhere. We use AI chatbots for homework or business reports, for pattern recognition in medical research, or even to make animals talk, like in a recently opened museum in Cambridge in the UK. In this episode, we dive into how large language models work and don't work, why they struggle with learning numbers, and why AI differs from humans doing the same. I am Regina Zielecke, and this is Deep Dive into Applied Science.
The idea of language models is not actually a new concept, but it was actually a very old concept. I think it was during the 1960s that the first language model was created. I think it was called ELIZA, where the idea was like it had certain built-in answers, and you give it a question and it would give the answers. And then like at one point you could see that it has become illogical. But then in modern times, new neural networks came into development which could be applied. Neural networks which could base their answers on like previous words. For example, you have a sentence, you have a word, and then it could predict the next word. But the revolution kind of came, I think, in 2017 when Google developed this paper, which is called Attention is All You Need, where they gave the idea of something called a transformer, which used multiple of these so-called neural networks. And the way it works is, if I have to explain it in a very simple way, you have these toys where when you touch on one side, you have a pattern on the other side. So imagine that, but you put a machine in the middle. So you put input from one side, it goes through a lot of steps within, and it finds out similar patterns from that side to this side, and then it gives an output on the other side. So these large language models are trained on like huge amount of text, like you have books, web pages and everything. And given that they're learning on so many big amount of text, these texts are first, as you said, tokenized. By the term tokenized means it is broken down into different bits or small bits. And then these are formed into embeddings. By embeddings means these small tokens or these small bits are formed into some numerical structure, and they are put in some sort of space, or basic way of saying it, let's say you're putting it in a big chart with like numbers on it.
Like a coordination system.
Exactly, in a coordination system. Yeah. And then you have words which are similar to one another. For example, if you say Shakespeare and book, they have a close connection to one another because Shakespeare wrote a lot of books. But then again, you have the term book and a worm. In general sense, they might not seem similar, but there is a term called a bookworm. Hence, you will see them together. So this is how different in many ways the connections are created between them. And in this, like, let's say, multidimensional space, they have these connections created because of these embeddings. And given that, like, because of these embeddings, you have these different probabilities which are created. So, for example, if you ask, okay, who was the Queen of England, then it's going to give, and based on like what it can predict, it's going to say, okay, the Queen of England was Elizabeth III, and so on. So it works kind of like that.
Yeah. So basically, the probabilities are always dependent on the words that come before. So it takes what it has seen in the structure before and then goes through the masses of data it has seen and tries to predict the most probable next word.
Exactly.
Basically.
Exactly.
So really like improv theater where we just switch around and you complete my sentences.
Yes. Exactly.
Okay. Let's recap. A large language model trains on large amounts of natural language data, but a computer needs numbers to calculate and do stuff. So the individual words that are in the original data need to be tokenized and transferred first into numerical values. The abstract tokens are then embedded in the model based on their sequential probabilities in the data, and this is how the patterns or neural networks are identified. And because language represents our view on the world and its meaning, these patterns represent applicable knowledge, or as we prefer to call it, intelligence. But while chatbots can answer questions in full sentences that are seemingly meaningful, this form of intelligence is somewhat limited. They are only an improv partner, as Helen Toner already called it in Time magazine in 2023, or an autocomplete on steroids, as NYU Professor Emeritus Gary Marcus called it in the Washington Post. So let's take a closer look at those limitations. One is that it can't really, unless trained to do so, it won't acknowledge user intent. So it won't know what the human person interacting with it actually wants.
That's the thing. These large language models are trained on like massive amounts of data. So you don't know like what it can give out. So there are many ways to actually tackle these limitations, for example. So I saw this example a few days back, was like if you ask GPT-1, I think, like, what is Belgium? Then it's going to say it's just a barren land and village. And like as time went on, it like if you ask like, okay, what is Belgium? It's going to give like this beautiful paragraph like, okay, it has many historical heritage, blah, blah, blah. So the reason why I'm saying this is because it has no context as to what you want. So one way of tackling it is, firstly, if you're using a chatbot, then you could give it prompts saying that, okay, these are the specific things I need. So give that to me accordingly. Let's say, okay, in bullet points, give me 5 points regarding the geographical location of Belgium, and it's going to give you that, or something like that. Also, there's this certain thing called a fine-tuning. Mm-hmm. So what a fine-tuning does is you have the complete model, but you tell it to do, okay, I need it for these particular aspects. For example, someone who's working with medical data. So you can say that, okay, I have these symptoms. You, according to the medical thing that I taught you, you give me the outcome for this. And then that whole thing will be based for just medical purposes, for example. Or like recently, there was this thing that it passed a law exam.
So there's still those masses of data that are in the first step, the pre-training, and then in the fine-tuning, you just have a little bit of data that you feed extra.
Yeah.
That's sort of narrowing your purpose down.
Exactly.
Okay. Some of the other limitations are that obviously, you've said so in the beginning, the output depends on the input. If the data is harmful in some way or biased, as data usually is, when it's collected by humans, so will be the output. So the harmful characteristics of the training data will be given out. What I think is really funny to watch and has been quite popular on social media as well is to watch those large language models to hallucinate.
Yes.
So would you go into that?
Yeah, so the idea of hallucination is it's producing certain information which is not supposed to produce. For example, it could be that you give it a very complex situation and it was just going to produce some rubbish or gibberish or thing that you won't even understand. And this used to be somewhat of a very common thing. And to a certain extent, it still happens. Like you could say a very weird question that probably is not even in existence. Like you say, okay, give me a complex number of poems or something like that. It just won't know what to produce. But there is this thing called human interaction fine-tuning, let's say. I forgot the complete term for it. But what it does is, if it does produce an answer, it asks the human, like, is this answer correct or not? And so it's going to ask, like, okay, is this correct? And then if the user says, no, this is not correct, then it's going to produce a different answer. And like, it's going to go on like this till it, let's say, produces a proper answer. And the human says, yes, this is the correct answer. And the next time it's going to be asked that, it's going to then give out that particular answer.
I mean, that sort of requires that the humans themselves know
exactly.
the answers.
Exactly.
So basically, we transport our own limitations back to the model.
In a
we could
way,
say.
yes.
Yeah,
But then you have a lot of experts using it, so
that's true. That's thankfully, yes.
yes, hopefully.
One of those, well, I would classify this as a hallucination, and I think we're getting closer to your topic here. Is one example posted on Twitter a couple of years ago. So the input the user gave to GPT was Barbara, Mary, and Harry had red balloons. Ted had a blue balloon. Sam also had a red balloon. How many children had red balloons? And GPT answers, Barbara, Mary, Harry, and Sam had red balloons. In total, there were 5 children with red balloons. So what's going on here, and how does this relate to your topic?
So it's still learning. And I think like over, the last 1 month or so, in terms of numerical or more logical conclusions, it has become better. But it is still kind of difficult for it to go into more in-depth mathematical ideas. For example, if you ask it like, okay, give me the value of pi till the 1000th decimal, it probably won't be able to do it because it's a huge number, and it's still not capable of performing mathematical, let's say, calculations which are very complex.
And how does that relate to your PhD?
Okay, so what I try to do is like, okay, since we already have so much information embedded within a language model, I thought that, okay, maybe we could utilize that information to perform some sort of regression analysis, like predicting continuous values. Because beforehand, there have been papers which have done it with, like, let's say, binary classification. So I thought that, okay, we have different data sets which are quite complex. For example, you have data sets which has tons of text and tons of numerical. And if you're doing it with like the traditional statistical methods that we use, you have to do like a lot of not fine tuning in this regards, but rather you have to pre-process the data in different ways so that the model can understand it or do proper calculations. Whereas when you're feeding these sort of data into the regression model for using an LLM, you don't need to do all of this. You just feed it quite raw, basically. And given that it has the ability to understand complex languages, like be it text or numbers, it can understand that. Then you ask for predictions. Now, this is where sometimes problem happens, because since it's not completely capable of doing like difficult, let's say, calculations, it kind of gives out some erratic results, let's say. So my idea was in this regard that, okay, what if we change these numbers into a more text-related format? A very simple idea was that, okay, maybe, you have lots of continuous numbers. We maybe break it into small bins. And then...
What are bins?
I mean, small categories. So for example, I was going to say, so let's say you have particular variable which can take numbers from 1 to 100. So we say that, okay, 1 to 50 could be low and 50 to 100 could be high. And then instead of having like 1 to 50 and 50 to 100, we put in another information to the model saying that, okay, so let's say 48 is low, 79 is high. So you're giving it more information. As a result, when it comes to predicting, it can do better prediction, per se.
Okay, so it doesn't need to know that 76 is one step higher than 70. What did I say? 75?
Yeah.
It doesn't need to know that specifically, but it just needs to know where on the grand
on the
spectrum.
range. Yeah. Like the whole range. So,
okay.
I mean, I'm saying it in a very like layman terms, let's say, but like these categories could be even more. So for example, I could say, okay, 1 to 10, 11 to 20 and so on. So you could make it even larger so that it understands better. But I think like over time, it has learned to at least recognize numbers better to a certain way.
How do you know that the performance gets better?
So we use different evaluation metrics when we're performing these regression analysis. Things such as mean squared error and mean average error. And
so those are like standard
yeah,
statistic
these are
things
evaluation matrices.
Yes.
And the lower they are, the better. So when you first perform those, it's quite high. But when I've used my methods, it has come down. But this has come down. This has come with, of course, some limitations. When you're doing these regression methods using traditional methods, you have the power of interpretability, whereas using these models, you cannot really interpret why things are happening. Yes, the model is improving, you're getting better predictions, but you don't know why these things are happening.
So basically, we go back to the beginning of the limitations of
Yes.
large language models
Yes.
in general.
Yeah, but I mean, this is the case of any modern, let's say, neural network problems. So there's this fine line between, let's say, what we say statistics and data science. Whereas data scientists mostly try to predict and get the best model or prediction. And us statisticians try to understand why these predictions happen. So, I mean, yeah, it's actually very like a trade-off kind of. Like you might get the best model, but you might not be able to say why these things are happening. But when it comes to statistics, it's like, okay, you've got a good model, good, but justify it. Why is it good? It's kind of like that.
Okay, and you're trying to like combine these
Yes,
two.
so yeah, bringing basically both of them together, which isn't the easiest task, let's say.
Yeah, sounds like it. Lacking any sense of context or intention, even a model trained on good data can only produce data that, while statistically plausible, may also be false. Without improving or fine-tuning the model to perform a specific task, it fails. And in the case of handling something as complex as the numeric system, it gets overwhelmed and starts hallucinating, almost like humans. The problem that Abra wants to solve in his PhD research is that, on the one hand, more data doesn't actually make models work better. In fact, less data regularly outperforms more data, so it's all about providing the amount of information that is just right, like dividing numbers into rough categories. On the other hand, the numeric system in and of itself is so complex that fine-tuning it requires understanding what these categories have to look like. So maybe if we want to find the best way to make AI learn to handle numbers, we should take a look at how humans do that. So for our next part, we invited developmentalist Daniel Ansari to dive into that.
Nice to be here. My name is Daniel Ansari. I'm a professor and Canada Research Chair of Psychology and Education at Western University in Canada.
So would you like to tell us a bit more about how this whole concept actually develops in humans? Like, how do we understand numbers? How do we conceptualize them?
Yeah, so there's of course a variety of perspectives on this, but from a sort of cognitive neuroscience, cognitive psychology perspective, I think we have a wealth of data to suggest, as I alluded to earlier, that we share with other species basic intuitions about quantity. Whether they are numerical in content is something that is still debated. But some people argue that they are numerical in content. I tend to think that is not the case. But let's just assume they're numerical in content. Then it's been argued that we learn the symbolic representations that we've invented by connecting them to the pre-existing intuitive representations of quantity, and that we go beyond essentially these more rudimentary coarse representations. So, for example, there's work demonstrating that 6-month-old infants, Fei Xu and Liz Belke showed this back in 2000, 6-month-old infants can discriminate between 8 and 16 dots, but they can't discriminate between 8 and 12 dots. So they have this sort of approximate sense of number. And nowadays that's called the approximate number system. And some people argue that this approximate number system is what forms the representational basis of our symbolic math learning. My position is a little bit different. I argue that the approximate number system exists, but symbolic numbers are something that's deeply cultural and that's passed on through generations. And we just need to look across the globe and see that there are cultures, that are remote cultures that don't have fully fledged economies, that don't have a fully fledged symbolic number system. They might have number words for 1 to 3, but after 1 to 3, they just refer to many, many more, one hand, two hand, because they just don't deal with large numbers. There's no necessity, there's no pressure on them to deal with large numbers. It doesn't mean that they're not capable of learning it, they just don't have the environments that foster that. So, and some of our research also shows that once children learn number symbols, it shapes the way they process quantities in the world around them. It's almost like an attentional filter. That's what we're still trying to figure out. So for now, we know we did some longitudinal work with kids between the ages of about 5 and 7. And we tested them on various tests of like dot discrimination, but also symbol discrimination. And you might assume that dot discrimination drives symbol discrimination. That would be sort of the most intuitive way of thinking about it. But it's actually the other way around, that, once you learn symbols, you could become better at dot discrimination. So we think, and we don't have the data to really say this is ultimately what's going to turn out to be true. But my hypothesis is that when you start developing symbolic representations that are extremely exact, that you view the world around you much more numerically. So when you look at a set, you don't just say it's a set of stones, but you might say it's about 10 stones. And that's because you have that symbolic reference that kind of guides your perception. We know that knowledge in general, in cognitive science, we know that knowledge influences the way we perceive the world, where our brains are predictive machines. We're constantly making predictions on the basis of what we know and what we've learned. And I think learning about numbers for children also gives them a way to make predictions about things in the world around them.
So first we have an approximate number system that gives us basic intuitions about quantities and the ability to make rough decisions that may or may not pan out. And then we learn a more specific, but also more abstract symbolic representation in the form of numbers. That helps us make more accurate predictions. That does sound quite similar to what Abra is teaching AI. Basic pre-training followed by a task-specific but abstract fine-tuning.
For example, me as a statistician who works with a lot of numbers, we have to predict a lot of stuff. So for example, you have certain conditions and you say, okay, what would the output be in that regards? So for example, in regression and stuff. So I thought that, since these large language models, these are trained on like huge amount of data. So let's see how well these models work when it comes to doing the same thing. So when it came to kind of asking it to generate outputs in terms of numeric values, they weren't doing quite well. So then because computers don't learn the way that we humans do or understand the way that we humans do. So I thought that, maybe I could specify it in a textual way, then maybe the outcomes could be a bit different. So what I did was that, when I'm teaching these models from the data that I already have, I'm telling it, in terms of numbers, let's say instead of going directly numerically, I would say that, in forms of text. So for example, I would say that, the output is high, medium, or low. And then I would say that, let's say from this range to this range, it's low, this range to this range, it's medium, and this range to this range, it's high. As a result, it has a better stepping stone in terms of learning. And when I did that, it kind of gave a much better prediction.
That's really interesting. I have to confess that I don't know a lot about AI. I'm like most people in this world, just sort of dabbling a little bit with the large language models. But I did read that they aren't particularly good at math. It's interesting that you say that you sort of give them intuitions about quantity, right, rather than precise number. And I think that is something that we know from the research with both humans and non-human animals, is that we, I think, have a sort of evolutionary grounding in some basic intuitions around quantity. They're fairly imprecise, and maybe they form our basis of our more precise number abilities. One question I would have for you, Abrar, is, I'm a developmental psychologist, so I think about development. Large language models don't really develop, do they? They are already developed because they already have so much knowledge, quote unquote knowledge. So how do you see that? This is always a problem when you're trying to simulate something in a computer environment, whether that be a computational model or be a large language model, is how do we actually, if you really want to compare the two, do you see any scope for building sort of development into that?
I mean, of course, there's always scope for development. If you compare how these models were, let's say 2 years back. So this idea of whole large language models came about, I think, in 2021, 2022, when OpenAI created its first GPT model. And it was, I think, the GPT-2, which was available. So if you use that, and if you use, like, let's say, the Chat GPT right now, it's like this huge difference. And the reason for that is so these models are trained on massive amounts of data, right? And the more data it's been trained on, the more number of, let's say, what we call in science, like parameters are formed. And the more number of parameters that we have, the better it is in terms of like conducting a work, let's say. So for example, before you could ask it certain questions and it would give an answer, but like midway through it would get lost, like what it's saying or what it's trying to say. But now it can literally give you like a huge essay, for example.
I guess my conceptualization of development, I don't just mean that it gets better and larger and bigger. It's more if we're trying to understand the parallels between humans and AI. Humans go through a process of development that is both physical and mental in nature, right? And children learn by interacting with their environment and learn by interacting with others. So the way, I guess what I'm trying to say is that the way that a large language model learns is maybe not quite the same as a human child. So then try to understand the parallels, like you and I are trying to understand the parallels. There is a fundamental mismatch in the way that knowledge is acquired and knowledge is built.
Yeah, no, so basically creativity is one of the differences, and what you already mentioned, AI as a closed system, the model that it feeds is closed in itself, and you spoke of interaction, which is highly important for human development, right?
Exactly. Interaction with, with the child, with the physical environment, and the child with the social environment. In the domain of math, of course, interaction with the physical environment is really important, right? Through the idea in math development is that children start out with very concrete representations of quantity and numerical value, and then gradually go away from concrete to more representational, and finally to the abstract level, which of course is a level of sort of human cognition that is perhaps unique to the human species and is something that is quite recent in cultural history. 8,000 years ago, we didn't have fully fledged symbolic representations or a number sequence. These are inventions, and you talked about inventions, and how we've gone beyond that, how mathematicians have even invented more complex things. So those might be some interesting differences to consider.
The problem with computers, or not computers, but these models in general, is like, when you're teaching them a model, so when you're teaching them numbers, they don't take them as numbers, but just random symbols. Mm-hmm. So when you tell them that, okay, 2 + 2 is equal to 4, for example, so it's now embedded in its memory that, okay, if someone provides me with a data of like what is 2 + 2, then according to my knowledge, probabilistically, this is the output that I should be giving. Mm-hmm. Hence, it doesn't know what these numbers do, but rather it more gives us an idea of what it has already known. And another issue is like, okay, I'm still working on it, but now like it has gotten to a better situation, I would say. So when you provide in certain variables, it tries to kind of logic with things. Since it's learning these things more in symbolic way, it still doesn't know what the real meaning of these values are. It's mm-hmm. just a probabilistic idea of what it could be. So that's an issue.
Mm-hmm.
Yeah, that, I mean, the idea that we can use computers to understand human cognition is not a new one. It's not unique to large language models, but it has a long history. And I think that we're probably not going to be able to find big similarities between humans and machines, but what machines have always been powerful for is simulating the way that humans learn. And through those simulations and models of human learning, we can generate testable hypotheses about the mechanisms of learning. But new deep learning models and all that kind of stuff, it tries to approximate the neural system a bit more. So I wonder how large language models play into that, whether they play into that at all. I have no idea.
Yeah, I mean, these large language models do play around with the idea of neural networks. So large language models are a more, let's say, advanced version of these neural networks. They work on the basis of transformers, which is a sort of deep learning method, but a more advanced one. And the idea is, instead of deep learning models where you just put in an input and it gives an output, what it does, it takes in an input, it gives an output, and then it goes back into another input and then gives another output. As a result, it parallelly does two things, which kind of makes it similar to how a brain works, but in a much more vague sense, let's say.
When I try to summarize from what I've heard from you two, basically we don't really, we will never have an AI that is learning in the same way as humans do, but we can learn from AI about how humans learn in distinguishing the differences between both outcomes and the parameters that come into play.
I mean, so I would say that the initial stage of how children are being taught and how AI is being taught in general is the same. So when a kid is born, they literally know nothing. And then you give it information. That's what's, let's say, feeding the AI with lots of data. Then it goes through something called reinforcement learning. So if a child touches something hot, he knows not to do it the next time around. And it's similar to that of an AI model. So we have this concept of rewarding. So if it does something right, we give it a reward saying that, okay, you get 1 point if the answer is correct, and if not, and it learns in that way. And of course, there's also this concept about teaching these large language models that, okay, when it makes an error, the humans can come and fix it. Whereas it's kind of the same for the children as well. So if they make a mistake, you say that, okay, no, this is how it's done.
This was wrong. Yeah.
The one thing that I would disagree with you is that the humans, it's not true that humans don't know anything when they're born.
No.
We are born with quite sophisticated pieces of knowledge that we don't have to be taught. They range from knowing things about objects, surfaces, about depth, about height, and to some extent about quantity. So I think we have a lot of priors in our neuronal systems. And those priors may not exist when a large language model starts to learn. A large language model is kind of a blank slate, as far as I understand it, when it starts out. Whilst humans have priors that have been, structured through the process of evolutionary adaptation and help us to survive, right? So I think there is a difference there, and it's an important difference because these priors are influential in terms of what we learn and how we orient to what we learn.
Yeah, of course. I mean, it's already a pre-trained model for the humans, they already come built in with that.
But isn't this also maybe a very important difference that the large language models come with all the data at once, whereas learning for humans is incremental?
Yeah, that's what I was trying to say at the beginning, right? That as a developmental psychologist, I always think about the mechanism of development and developmental changes being fundamental to the human experience and to human learning and cognition. And that doesn't apply to children, it applies to adults as well. Unfortunately, I'm on the other curve now where things are going down, where rather than sort of offering advantageous constraints now, my knowledge and skills are declining and my ability to learn is declining, but I'm still developing as such. And that's maybe a constraint that isn't built into large language models. But that's where we get back to the point that large language models can help us simulate human cognition, but they do not resemble human cognition necessarily. They might look like human cognition in their output, but that doesn't mean that the mechanisms that generated that output are the same.
Yeah. One thing that I always tell people, I mean, of course, there is some sort of fear mongering going on that AI might take over people's jobs and stuff. But I say no, I say the opposite. It actually makes people's life easier. So I would say in terms of reaching superhuman levels, of course, it's not there, or even human levels, let's say it's not there. But whatever it does quite well.
We've got to embrace it to some extent, but I think embracing it critically, I think a lot about it in the context of education, where a lot of people make grand claims about AI kind of replacing education and everything will be personalized to the student. But returning to one of the topics we had before, human interactions have certain characteristics to them that are never going to be there in a machine-human interaction context.
Yeah,
I mean, people also thought that the internet itself will replace learning and school. So we've seen how that turned out.
Been there.
Yeah. Thank you very much for joining us in this episode on AI. I hope you enjoyed it. I sure learned a lot. So thank you very much.
Thank you as well.
Thank you.
Yeah, thank you. Thank you. It was a great chat. Thanks for having me.
Thank you for bringing us over.
Thank you for listening in on Deep Dive into Applied Science. I hope you enjoyed our first episode in this discussion on learning numerics from both perspectives of cognitive and AI research. If you did, tune in for the next episodes, which will be released once a month from now on. This podcast is produced by Trier University of Applied Sciences within the GEORUP project, Graduate International Research Opportunities, funded by the German Academic Exchange Service. Editorial and production, Regina Zielecke. Design, Celine Bohner, Marie Abramovic, Bastian Franz. Post-production, Philipp Köhn of Hummelblume.